A quick polarity review.
Recall that polarity is the upward or downward deflection of the waveforms that appear on our screen, and this is how we can define a waveform as positive or negative in terms of what is being recorded at the scalp. So when we discuss polarity, we have to remember that there are two inputs into each amplifier channel, one positive input and one negative input, and the amplifier is represented as a triangle. There's an output which produces either an upward or downward deflecting waveform. As we know, a differential amplifier will find the difference between the positive and negative inputs and will amplify the difference. Whether that difference is a positive or negative value determines whether the resulting waveform will point upward or downward. Let's look at an image and visualize the process. Taking SSEPs, for example, when we stimulate sensory neurons in the body and that signal is received in the cortex, a small area of cortical neurons experiences postsynaptic potentials. So we can record this with precision with one electrode. And by convention, our active electrode is plugged into the negative input of the amplifier. Let's call it -3 microvolts. And remember, the differential amplifier subtracts negative information from the positive information. Let's say for simplicity, your positive electrode in this case was placed at FPZ and it recorded 1 microvolt. So 1 minus -3 gives us an output of +4, which tells our equipment to point the waveform upward. You can imagine if the electrodes were plugged in the reverse order, the -3 minus 1 would yield an output of -4, and the waveform would point downward. So in summary, the polarity of the output signal depends on the input signal itself and the input terminal to which it is applied. Remember that because we usually can't get an electrode deep into the cranium to record directly from the brainstem, our brainstem waveforms, technically waves 2 through 5, are far-field waveforms recorded from scalp electrodes. In fact, these brainstem potentials can be recorded from anywhere on the scalp, so it's important that we use a scalp to non-cephalic montage for recording brainstem potentials. Otherwise, if both electrodes were located on the scalp, the differential amplifier would subtract the information from itself and the output would be 0. It just so happens wave 1 is best recorded from an ear electrode like A1 or A2, whichever is ipsilateral to the stimulus, and those electrodes work for us as non-cephalic reference electrodes when we record brainstem responses. And finally, what's the polarity of these waveforms? Well, using an A ipsilateral to CZ montage, if the active electrode for wave 1 is the A ipsilateral electrode and the active electrode for waves 2 through 5 is the scalp electrode, then we know that our waveforms are being actively recorded by two different inputs of the amplifier. The AI electrode is the negative input and the CZ electrode is in the positive input. Remember, the differential amplifier will subtract the negative input from the positive input. So a more negative polarity waveform recorded in the negative input with none of the same information recorded in the positive input will result in a positive output, which creates an upward deflecting waveform. And this is the case with wave 1. Then, a bit later in latency, a series of positive polarities are recorded in the positive input with none of the same information recorded by the negative input, and this also creates an upward deflecting waveform. This is the case for waves 2 through 5. So in review, wave 1 has a negative polarity that is recorded by the A ipsilateral electrode in the negative input, and waves 2 through 5 have positive polarities that are recorded by the scalp electrode in the positive input.